Let's continue on with limits, and so let's talk about the rules of limits. And we're this video we're going to be looking more at how do you find a limit if you're not necessarily given the graph, and we could also extend this to kind of general, without an explicit function. If we just generally speaking, if we have a function, what can we do with the limit? So this first one, if k is a constant, then the limit as x approaches a of this function k equals k. So, and that kind of makes sense. So I won't do this for every example, but if you have f of x equals k, that is just a horizontal line. And so wherever a is, so let's just put a here. So obviously we're just coming to this value k when we get there. So, so the limit of a constant function is just a constant. Then the limit as x approaches a of k times f of x, we can pull the k out. So you can pull the constant out and just have the limit as x approaches a of f of x. And then that's going to be a, so we're just going to call this k times capital A. And then as we get to it, limit as x approaches a of g of x is b, limit as x approaches a of f of x is a. So we'll use those as we go, but we really don't even need those too much. So all right, so here we have f of x plus g of x, or f of x minus g of x, doesn't really matter. And so what you can do here is you can split up these limits. So limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x. Same thing with multiplying. So we can split the limit up when you're multiplying functions. So times limit as x approaches a of g of x. And of course, this assumes, well, we're x is going to the same value in both of these. So if you have different values, you can't go the other direction. All right, division, same way. Limit of f of x divided by the limit of g of x. So using all the arithmetic operations that we have, you can split it doesn't change the limit transfers, I guess you could say. If p of x is a polynomial, polynomials are always continuous. So really, if p of x is a continuous function, you probably could say this, then the limit as x approaches a of p of x is just going to be p of a. So really you can just plug in a into the function. If it's continuous, you can just do that. All right, for any real number k, so now we have f of x raised to the k. Then you can put that limit inside this exponent function. So you can find the limit of the function first and then raise it to the k. So that also works. Limit as x approaches a f of x equals the limit as x approaches a of g of x if f of x equals g of x. Then the limit as x approaches a b to the f of x. Now we can put this limit up in this exponent and say b to the limit of f of x. And then same thing with the log. So we had limit of the log of f of x. We can say this is log base b of the limit f of x. And there we go. So you can move these limits around. Probably anything that you think you can do, you probably can do when we're in this class. So we're not going to get too complicated with these limit functions. All right, so let's see an example of this. So we have the limit as x approaches 2 of f of x is 3, and then the limit of g of x is going to be 4. So we need the limit as x approaches 2, f of x plus g of x squared. So we could split this up. So limit f x approaches 2. And actually, probably the easiest thing would just be to plug these in. So 3 plus 4 squared is 49. and this is just a constant, so this would just be 49. Doesn't really matter what that is at that point. Okay, so basically you just plug these in, plug in whatever f of x is, plug in whatever g of x is, and then simplify. All right. Okay, so let's look at this one. So this is a rational function. Rational functions are not continuous everywhere. They're continuous most points, but typically when we're asked to find the limit of a rational function like this, it's going to be at the point where it's not continuous. So to kind of show this in what I would suggest, whenever you have a limit problem, plug in. Well, we don't really need that, but let's just plug this in. So plug in -3. -3 squared minus -3 minus 12 over -3 plus 3. Now the problem is you get, so that'd be 9 plus 3 minus 12 over -3 plus 3. So you end up with 0 over 0. So this is called an indeterminate form. Indeterminate forms, so that doesn't work. So you can't do 0 over 0. So you got to do something else. So we'll learn a few techniques as we go along for finding limits. The first thing you could try is you could try factoring this numerator. So let's factor the numerator. So x minus 4x plus 3. And now you can see that x plus 3's cancel out. And so we said the limit is x approaches -3 of x minus 4. This is a polynomial. It's a continuous function, continuous everywhere. So now we can just plug it in. -3 minus 4, and we get -7. Okay. So now what this graph would look like, it would be this function, x minus 4, but we would have a hole. So x minus 4, so that's like this, y-intercept of -4. And so at -3, we are going to have a hole in the graph. So if you were to graph this on Desmos, and I would encourage you to do this as you're doing these calculus problems. You're not allowed a graphing calculator on the test, but you should utilize the graphs in the homework to kind of reinforce what we're learning and build your confidence that mathematically you are doing the correct thing. So if you were to graph this on Desmos, it would look like this, where you have a hole here. It's just a linear function. So no asymptote on this one, because the x plus 3 cancels out. So, but generally speaking, when you're finding limits of functions like this, try plugging in the number, because sometimes you plug in the number and it just works out and you don't really need to do anything else. If you can plug it in, you get an answer. That's fine. If not, then you need to do something else. And so here's the first thing you learn how to do, which is factor the numerator, see if anything cancels. So if something cancels, that's probably a good thing. All right, let's talk about limits at infinity. And so this makes sense if you think about it. So if you have x going to positive infinity, so x is a really big positive number, million, billion, trillion, so on. What happens when you have 1 divided by a really big number, and then you're even raising that number to some exponent, so positive exponent. So now you have a billion squared, trillion squared, so on. X is going, or 1 over x to that exponent is going to 0. And then same thing if x goes to negative, so 1 over a big negative number is also going to 0. So you can see this, the 1 over x is the red graph, the 1 over x squared is the blue graph. And so obviously if you square x, it's always going to be positive. So 1 over 100 squared, 1 over 10 squared, so on. These are the values that you get. So as we keep going, x is going to go to 0. As we keep going, we're going to go to 0, and same thing in this direction. So just think of it more as it's 1 over a really big number that's going to get smaller and smaller as that x gets bigger. Okay, so how do we find this? Essentially what we're doing here is finding the horizontal asymptote. And so you could think of it in that way, but a better way to do this is it's not really the proper way, I guess you should say. So if you plug in infinity, which you can't really plug in infinity, but imagine you're plugging in big numbers, what are you going to get? Well, it depends on the number that you plug in, of course. But you're going to approach a number. Now, the way to do this is to utilize these two properties here. Pick the biggest exponent. Pick the biggest exponent. And divide everything by, in this case, the biggest exponent is 2. So divide everything by x squared. So we're going to divide each term by x squared. So 2x squared divided by x squared is 2. 3x divided by x squared is going to give us 3 over x. 4 divided by x squared doesn't really simplify, so 4 over x squared. 6x squared divided by x squared is 6. Oops, it should be a minus. Negative 5x divided by x squared is going to be minus 5 over x. And then plus 7 over x squared. So now, when x is really big, we're going to get we'll get some answers. So we're not going to get the 0 over 0 or anything like that when x gets really big. So now imagine x is going to infinity. So x is 1,000, x is 10,000, x is 1,000,000, on and on and on. What happens? This number goes to 0. 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 So when you're plugging in bigger and bigger numbers for x, these 4 are all going to 0, and then these 2 are staying the same. And so that means that this limit is 2/6, or reduce it down to 1/3. Now, if you remember from when we talked about horizontal asymptotes, how would you find the horizontal asymptote of this? Well, you look at the degree of the polynomials. That degree is 2. That degree is 2. And so they're equal. So you look at the ratio of the coefficients, which is 2/6, which reduces to 1/3. So we're doing the same thing. That doesn't always work. So we could come up with functions. If you start putting square roots in, then that gets a little bit trickier. So you don't want to rely on this method. This is the better way to go now that we're in the calculus part of this. Okay, so maybe watch these videos a couple of times if you need to understand the concept and be comfortable with the different techniques and how to think about this as we go along.